Now we have an example problem where we need to calculate solidification time for a die casting. And the solidification time for a die casting, one model is that the time equals the density of the metal times the latent heat of fusion of the metal plus the specific heat of the capacity of the metal times the superheat divided by the heat transfer coefficient. So this is important. Heat transfer coefficient. For die casting, the heat transfer coefficient is what controls the flow of heat from the metal into the die for solidification, and it's much more rapid than in sand casting. And then the difference between the melting temperature and the die temperature is what drives that time reduction down, multiplied by the volume over area ratio. So if we do an example problem similar to what we did for sand casting, where we have our casting as a block shape, 50 by 200 by 100. So for this shape, we've already calculated the volume equals 0.001 meters cubed, and the area equals 0.07 meters squared. And then we need the density for the zinc, 7,130 kilograms per meter cubed. Need the latent heat of fusion of the zinc, that's 101,000 joules per kilogram. We need the specific heat capacity of the zinc, that's 388 joules per kilogram Kelvin. We need to decide for our problem what's going to be the superheat. I'm going to keep it the same as I used for the sand casting. So that's the pouring temperature minus the melting temperature would be the superheat. So it's liquid. That's how long it takes before it hits the solid. 100K is what we're going to assume. Then our heat transfer coefficient for this die casting process, we're going to use 800 watts per meter squared Kelvin. So that's same as 800 joules per second meter squared Kelvin. The melting temperature of the zinc is 693 Kelvin, and we're going to assume a die temperature of room temperature. In reality, these dies heat up. So this T melt minus T die. So we've got a little bit above room temperature, but not much. So in reality, they would be hotter than that, but we're just here to make the math easy so we can understand the concept. So that difference is 400K. Let's plug all this into our equation, 7,130. We have to keep the units because making sure the units cancel is very important. 101,000 joules per kilogram here. The metal, the zinc, 388 joules per kilogram Kelvin. Specific heat capacity times the delta TS, the superheat, 100 Kelvin. The H is 800 joules per seconds meters squared Kelvin. And then the difference between the melt and the die is 400 Kelvin. And then we have V over A, 0.001 over 0.07. Let's look at how our units are going to shake out here. First, let's go inside this term. Kelvin and Kelvin cancel. So now we're adding joules per kilogram with joules per kilogram. So joules in the top is going to cancel with those. Joules in the bottom. Kilograms is going to cancel with those kilograms. Now we've gotten rid of everything in here. Meters cubed. So we still have, let's see, that Kelvin cancels with that Kelvin. This is going to be the leftover from meters cubed per meter squared is going to be meters. So we end up with this meters cubed is going to go up on the top. So meters cubed per meters cubed. Those all cancel. So we end up with just seconds, which is what we want. That's going to go up on the top because it's in the bottom of the fraction on the bottom of the fraction. Now we plug all this into our calculator and we're going to get a value of 48 seconds. That's our solidification time for this zinc die casting example. Now here's a follow-on thought question. If you double the heat transfer coefficient, what is that going to do to the solidification time? The H is right here. So if I double this, it's going to reduce the solidification time by half. So the old solidification time, TS old, is going to be twice as much as the new solidification.